As you guys know, I work on VMD as my day job here, and in VMD, the things we've been trying to do, in particular, make things that used to be sort of non-interactive calculations into things that we can do either interactively or at real time. So that's sort of what I talked about the other day. And the calculation and display of molecular orbitals from quantum chemistry simulations are one of the key things that we wanted to accelerate relative to the way they used to perform. And so I'll tell you a little bit about how we do that. So calculating these orbitals involves evaluating the orbital amplitudes on a regularly spaced lattice, and then walking through that lattice and computing isosurfaces, which are then displayed on the screen. And doing this even with multi-core CPUs, even using SSE, takes tens to hundreds of seconds, even for a very small system like this. Just to give you an idea, the kind of speed-ups we can get using the GPUs for this calculation, if I compare the performance of VMD versus two of the popular tools, Molecular and Macromolecular, we have also done a lot of work making our CPU code fast, but relative to Molecular, Macromolecular is about 2.5 times faster. VMD on the CPUs is about 12 to 16 times faster, and the GPUs are about 200 to 500 times faster. So this is a big increase in performance. Just relative to our own fastest CPU code, we get very significant speedups. And so I'm going to tell you today a little bit about how we achieve that. So we have several different algorithms, but the fastest of these algorithms is, at least for the broad range of GPUs that we want to support, it basically uses that on-chip fast constant memory to store all the orbital coefficients and arrays that we need to process, because it's read-only data and we're just going to have all of the threads walk through the same data. And using up to 4 GPUs, we can get speedups on the order of 276 versus one CPU core. That works out to something in the 40s or 50s versus 8 CPU cores. So our goal is basically to accelerate these calculations to the point that we can animate these structures at a rate of about 10 frames per second. If we could do this, this would give us the same ability to display time-varying simulations that we've had for molecular dynamics for decades, but have up till now been impossible for molecular orbitals. The way this is done, I don't know how much you all know about quantum chemistry, but basically we read a simulation log file produced by a quantum chemistry program like GAMES. This gives us a bunch of molecular orbital coefficients, basis set, all the atom coordinates, things like this. We load these things in, and we do a bunch of sorting to organize these coefficient arrays so that when we process them within VMD, we walk through them in a consecutive order. And this is one of the things we do that gives us the performance on the GPU ultimately. So this sorting only takes a few, maybe 5 seconds to do all that work. But once that's done, we've organized the data in such a way that when we actually do the calculation on the GPU, all those on-chip memory systems will give us their peak performance. So we're doing things like finding all the unique atom types, getting rid of duplicated coefficient arrays, things like this. A lot of the quantum chemistry programs, their default behavior is they just emit all of this data, even data that's redundant, in their simulation log files. And so by removing all those redundancies and sorting things and getting them as compact as possible, it gives us a better chance of being able to fit the critical parts of these coefficient arrays in those small on-chip GPU memories. Once we've done that, basically that's sort of a one-time thing that happens when the program starts. From that point on, we basically go through a loop where the user interacts with the program. Either they're manipulating the visual display of those molecular orbitals, changing various parameters, which orbital they want to see, the resolution of the orbitals, whether they want a particular spin or things like that. Every time they change one of those parameters or they change the time step in the simulation that they want to see, we have to recompute this molecular orbital grid. And so we retrieve for every time step the particular molecular orbital wave function coefficient array, and we then recompute this grid. Once we've recomputed the grid, we extract an isosurface mesh, which is a bunch of triangles, and then we draw it with OpenGL on the screen, and then we repeat this over and over and over. One of the key things that we do to make this fast, I don't know how much you guys have seen in the talks up to date about using multiple GPUs, but one of the issues that you encounter with using multiple GPUs is that when you create a host thread or a host process and first attach to that GPU that you want to run your calculation on, there is usually a tenth of a second all the way up to, in some cases, several seconds of delay when you first attach to that GPU. And the magnitude of that delay depends on whether or not the GPU is attached to by a windowing system. So for example, if you're running on a cluster and X Windows is not running on the node, that GPU will be put into sort of a deep sleep, and when you first try to talk to it, there is a huge delay while it sort of wakes up and the driver brings it up to its normal operating clock rate and all these things. And if you were to basically create the worker threads that we wanted to use to do these calculations over and over and over, if we waited and created those threads just at the moment when we needed them, we would incur this huge startup penalty, in particular on machines where some of the GPUs are sitting there idle and have gone into this deep sleep sort of mode. So one of the first things we do is we create a pool of worker threads on the host, and those threads are then associated with a particular GPU, and we keep them around for the entire runtime of VMD. So once we've created those threads, they're persistent, we keep them around, and then we put them into sort of a sleep loop, the host threads. So we have them waiting on a little, what we call a barrier synchronization object, and it's designed in particular to allow them to go to sleep so they're not sitting there spinning, checking if there's work to do. And so they basically go to sleep, and what happens is every time we need to do a calculation, we sort of ping them and wake them up. So it's got the same issue of there's a tiny amount of latency, but the difference is we're talking, it takes a millisecond or less to wake up these host threads and wake up their associated GPUs, so long as they remain in this initialized state. Whereas doing that, if we created the threads on the fly, we'd incur a tenth to several seconds of delay every single time we wanted to do a calculation. So this is something important for interactive calculations, like the types of things we want to do very much in VMD. We have to take this approach of having a pool of worker threads sitting around sort of ready to go. So I don't know how many of you are going to work on projects of that type, but that's something to be aware of. Also, if you do timings of GPU calculations that involve multiple GPUs, and particularly in the case of clusters where there's no windowing system running, when you first talk to that GPU, there will be a big delay. So you need to write in your code, if you're going to do benchmarking of your GPU code, you should have some sort of warm-up routine that basically pings the GPU and either copies some memory to the GPU and back just to verify that it's actually all the way up, and make sure that your timings don't begin until after the GPU has been fully initialized. And then you'll get much more accurate timings of your code. So our molecular orbital calculation, as I described, we have this regularly spaced lattice. Usually it's very finely spaced so that we get very smooth surfaces. The nice thing about this calculation is every single one of the lattice points can be computed completely independently from the other. So there are no data dependencies between these lattice points at all. It's very similar in many respects to the direct Coulomb summation kernel, because the calculation scales quadratically. These exponential functions that describe those molecular orbitals decay very rapidly. So there's definitely an opportunity for us in future work to basically use one of these cutoff techniques to truncate the influence of atoms to a region that's constrained by some sort of binning strategy. The difficulty is there isn't a single cutoff like we have in the potential cases. These orbitals, the particular region of influence where there's a non-negligible contribution can be either very small or some of them, it could be the entire volume will be affected. And so it's not as straightforward. We can't have a simple single tile size binning strategy that's been highly optimized for a single case like the one we described in the cutoff code in the workshop last week. This case is a little more complicated because those exponentials, depending on what the coefficients are, the scaling function, scaling factors, and so on, they may have either very broad support or they may have very narrow support, and so it's just a very data-dependent scenario. We will have to come up with a scheme that sorts them probably according to the exponent magnitudes. So we can calculate all these independently. Just like with the electrostatics codes, we use a very similar scheme where we take the grid dimensions of interest and then we pad them out so that the region that we actually compute on the GPU is an exact multiple of the dimensions of the thread blocks, and it's a multiple of the coalescing size. And so exactly as we've described before, we have a little padding region at the edges, and then these results are typically just discarded. And so we do the work to compute them, but we throw them away. For calculation on multiple GPUs, since all of these lattice points are independent of each other, we can basically launch planes of this grid independently. So we can calculate one slice on GPU 0, another slice on GPU 1, another slice on GPU 2, and so on. What gets interesting, though, is that in a lot of machines that people actually use, the GPUs are not all identical. Some are faster than others. Not all GPUs may even be able to do the calculation or to use the same kernel. One may run a faster version of the kernel than the other, depending on its hardware capabilities. This is probably less of a concern for codes that run on clusters, because on clusters the hardware tends to be uniform, for simplicity's sake and to give predictable performance results. But for visualization workloads like BMD that run on a desktop or laptop machine, which may have a couple of generations of GPUs in it, the ability to load balance these things is much more important. And so just to give you an example, we might have a scenario where we launch one of these tile or one of these lattice slices on a GPU that only has 2 SMs. A lot of the inexpensive laptop GPUs, especially now that they make laptops that have 2 GPUs, a low-power GPU and a high-power GPU, we may find both of them, but one may be much more capable than the other. And so we want to be able to basically dynamically schedule that work across those different GPUs.
Can I ask a question real quick, speaking of that?
Yes.
I remember from I think it was GTC saying that if your laptop has 1 GPU only, but it's a CUDA enabled, that you couldn't use that for CUDA.
Oh, you can.
You can?
Yeah, you definitely
was
can.
that something that they changed in the driver? Because I remember them saying you couldn't.
Boy, I don't know what they would be referring to, because you definitely can.
Okay.
Yeah, I don't understand why they would have said that. I would say this, though. Maybe this is a Windows thing. It could